Alright guys, we're looking at a problem today. I'll be honest with you, this problem looks a lot simpler than it actually is. We're going to go through this problem, but my initial take on this was like, it's going to be an easy problem, but it actually ended up being a little more involved than I expected. So do not worry if you're struggling with this sort of problem. Hopefully this video will help you. If you're looking just for an answer, a general answer to all these solutions, I will post timestamps for when the solutions come. Just look on the time bar and it'll tell you all that. But anyway, let's just get right into this. So we've got a heat pump and it has a coefficient of performance equal to 4.90 and it requires 1.86 kilowatts to operate. So the first question is asking us, given this information, how much energy does the heat pump add to a home over the course of an hour? So first and foremost, if we're going to solve this equation, we've got to know something about the heat pump, okay? This is going to be very important that you understand this. You probably do know this, but if you don't, I highly suggest writing this down somewhere. So the coefficient of performance for a heat pump, so the coefficient of performance of this heater is equal to the amount of heat added into the hot source over the work of the engine. So what this means is this heat up here is how much is added to the room that we're heating. So added to the room, and this is how much energy or work we added to the engine to produce the amount of heat in the room, right? So what we're saying is 4.90 equals the amount of energy added to the room over the amount of energy entered into the engine. Now, we know how much power is needed to operate this engine, right? We know that power of this heat pump is equal to 1.86 kilowatts. Now, what's a kilowatt? A kilowatt is just a kilojoule per second, okay? That's what it means to be a watt. It's a joule per second, and since we've got 1,000 of them, it's 1,000 joules per second. So that's how much power is needed to operate this. So in 1 second, we're using 1.86 kilojoules of energy to operate this engine, this heat pump. Okay? So over an hour, over the course of an hour, we're getting this much energy into it, because this is how many seconds, here's how many seconds there are per hour. So we're going to take the amount of power it takes to operate this per second and multiply that by how many seconds we're running it for. And since it's running it for an hour, we're going to be running it for 3,600 seconds. So when you do this calculation, you end up getting 6.70 times 10 to the 6 joules. That's how much energy is needed to operate this engine for an hour. This energy that we just calculated is not the amount of energy that's entered into the room. This is the amount of energy entered into the engine, right? So if we know how much energy we entered into the engine, how do we calculate the amount of energy entered into the room? Well, that's just the heat that we added to the room. That's how much energy enters the room. And from this formula up here, COP heater, the coefficient of performance for the heater, equals the heat added to the room over the work added to the engine. We can solve for that just by multiplying by work on both sides, right? So this equals the coefficient of performance for the heater times the work, which is just this number that we calculated, which is like saying 4.90 times that number we just calculated And when you end up doing this calculation, you get that the amount of heat added to the room is 3.28 times 10 to the 7th joules. That's a lot of heat added to a room, but we did that over a course of an hour. And this is going to be your final answer for part A. This is the final answer for part A. Now, here's the kind of hard part, the very theoretical part. Part B wants to know if the heat pump is reversed, so then instead of acting like a heater, it acts like an air conditioner or like a freezer, what would that coefficient of performance be? So, what it's asking is, if we're transferring this heater into a freezer, given that we know this, what can we say about this value? What can we say about the coefficient of performance of the freezer? So in order to understand all these different values, like QC and QH and W, we got to understand how it looks with a refrigerator, right? So what we're doing is we've got this engine here, some sort of machine, right? And we're going to call this our system. This is our system. Now, given this is our system, any heat that enters, any heat that goes into this engine is added heat. Any heat that leaves this engine is subtracted heat. It's negative heat. So we've got this engine, we've got this system. And what we're going to do is we're going to throw some work into it, right? So that's like adding gasoline to your car and then like combusting it within the engine. We're adding work into this system. And that work is going to take heat from this cold element. So we're taking heat out of the ice box, trying to make it colder inside the freezer. So we want this to be colder. So we take heat out of it. And we put it into this system, right? Put it into this motor, this engine. So we're introducing QC, that amount of heat, into the system. So QC in this case is positive because we've entered it into the system. And what we're going to do is this heat that we just added, that we took out of the freezer, it has to go somewhere. It can't just stay in the system, or else then the system's either going to get super hot and start breaking down and like melting and whatnot, or it's going to end up radiating back into the freezer, and that's not what we want. So we got to dump this heat somewhere, and we dump it into a hot reservoir, into a hot sink, something that's actually higher temperature than the freezer. So what we're going to do is we're going to take out QH from our motor, from our system. So QH in this example, the amount of heat added to the hot source, is negative. Although we're adding heat to the hot source, we're making it leave the system. It's going out of the system. So it's negative in that case because we're taking it out of the engine. So work is positive. We're adding work into the system. Then we're taking heat from this cooler, which is QC. We're taking that amount of heat. We're adding it into this motor, this system. And then we're taking some other amount of heat and we're making it leave the system, which is QH. We're putting it out into the air or outside or the room, whatever it is that you're throwing it out to. You just want to make sure that the ice box is cold and the rest of the area that's taking all that heat is going to be hot, right? So QC in this example is positive, QH in this example is negative, and the work introduced into the system is positive, right? So that's how this system works. So from that, here's a few things we can say. I know that's a lot to take in, so I'm just going to throw down some stuff for you. This might be very important for you to like put in your notes, to really study up on and kind of commit to memory. But here's how this works. So the first law of thermodynamics says that the change in internal energy is equal to the change in internal heat plus the change and internal work. That's the first law of thermodynamics. That's very important. If you don't know this, you need to know this. That is going to help you with everything. Now, because this is a cycle system, because what we're looking at, this engine, goes through a cyclical process, it starts at some point, it goes through some transition, and it comes back to that same point, because it's a cycle system, we can say that the change in internal energy that comes from up here, that's actually equal to 0. Because we're coming from this point, coming all the way back down, and then ending at that same point. So the amount of energy that we started with has to be the amount of energy we end with. So we can say that the change in internal energy is 0. And from that, if we look back at this first law, well, we can rearrange this equation to show that the energy, the heat of the system internally has to equal the negative work of the system internally. That has to be true. Because if we just subtract the work on both sides, we get that this is true. So we know that the internal heat of the system is equal to the negative work of the system. What about just Q internal? What is the heat of the system? What is the heat of the engine? Now, if you remember my explanation, we add the heat from the cold source, and we subtract the heat that's going into the hot source. Right? We're adding this amount of heat into the system, and we're taking away that amount of heat into the system. So, the amount of heat that's actually present within the system, Q internal, is just equal to the heat added from the cold source minus the heat expelled into the hot source. This is true because of the way the system works. So we know what Q internal equals, and we know what work equals. So, remember, we want to find what Q cold over the work internal equals, because that's going to be our coefficient of performance for the freezer. We want to know what this equals. And we know what this equals. We know coefficient of performance for the heater. Well, that equals 4.90. We know that. So how can we transform this equation into this equation? Well, here's a nice little thing. We can rewrite Q hot because we know its relationship to Q cold. We know that Q internal equals Q cold minus Q hot. So we can say that Q hot, that just equals Q cold minus Q internal. And all we did is just rearrange this equation up here to find Q hot. Now from that, we can plug in Q cold minus Q internal into this equation up here. And that's going to get us Q cold minus Q internal over work internal equals the coefficient of performance for the heater. Now this is not for the freezer. Remember, this is for the heater. As up here, it's for the heater. Because Q cold minus Q internal still equals Q hot. Okay? We haven't done anything different as far as the right side of the equation. It still equals the coefficient of performance for the heater. This is awfully close, though, to the coefficient of performance for the freezer. All we got to do is somehow get rid of this Q internal, and we'll have ourselves Q cold over work internal. And we know that equals the coefficient of performance for the freezer. So how do we get rid of the heat internal, the internal heat? Well, if we remember from the cycle system, Q internal equals the negative work internal. And we can plug that in, right? We can say that this minus negative work internal instead of Q internal over work internal equals the coefficient of performance for the heater. And simplifying, we can say that this equals the coefficient of performance for the heater. And if we split this fraction that we've got right here, if we split it up into its two parts, plus work internal over work internal equals the coefficient of performance for the heater, we see that this term here just equals 1. The work internal divided by work internal, that equals 1. So really what we're saying is the heat of the cold element divided by work internal plus 1 equals the coefficient of performance for the heater. Well, now we can solve. We can say that this term equals coefficient of performance of the heater minus 1. And if you remember, this guy, that just equals the coefficient of performance for the freezer. And then to completely solve, we now have the coefficient of performance for the heater minus 1 equals the coefficient of performance for the freezer. So if we're turning this heater into an air conditioner, into a freezer, the coefficient of performance, which was 4.90, well, all we have to do is subtract 1, and that's going to give us the coefficient of performance for the freezer. And the same can be said for the opposite. If we're turning a freezer into a heater, all we have to do is add 1. So if we're taking your ice box in your freezer and we want to turn it into a heater, it's going to be a whole 1 level, a whole 1 magnitude greater in performance as a heater than it is as a freezer. And this is always going to stand true so long as our heaters and our freezers have that exact relationship. So in this case, since our coefficient of performance for the heater was 4.90, all we do is subtract 1, and we get that our coefficient of performance for the freezer is 3.90. Like I said, this problem is a lot more involved than it might seem on the surface, so if this gave you any trouble, just know you're not alone. It took me a long time to figure this out myself. I looked on the internet for a lot of solutions. I didn't find much. Best of luck to you guys in your physics stuff, and if you've got any other questions you want to post in the comments, I will gladly do my best to make a video on anything else you guys have issues with. Alright, good luck to you.